Welcome to part 3, my favorite part of the course. We're going to start with time of flight MRA, move on to diffusion weighted imaging, and then finish off with phase contrast MR venography. Here are the learning objectives. Let's start with some questions. Go ahead and pause the video and do your best to answer them. I'll go over the answers after I cover the relevant section. How does time of flight MRA, magnetic resonance angiography, work? Essentially, it's the opposite of a spin echo. Remember, a spin echo boosts signal from the stationary tissues and makes the moving fluids, i.e. in the arteries, appear relatively black. So that's the opposite of what we want to do in a time of flight MRA. What we want to do is make the arteries white and the stationary tissues black so that we can really easily see the arteries. So it's the opposite of a spin echo. So therefore, we don't want to use a spin echo. We're going to have a gradient echo, which basically means instead of putting that 180-degree radio frequency pulse in between 90 and TE, we just leave that out. That makes it a gradient echo sequence. So that's the first point I want to make about time of flight MRA. No spin echo, right? Because that's going to defeat the entire point. We want to make the arteries white. A spin echo would make the arteries black. How does time of flight MRA suppress signal from stationary tissues? Well, it's going to apply multiple 90-degree radio frequency pulses in short succession. So let's take a look at this pulse sequence diagram. We see multiple 90-degree radio frequency pulses in short succession. This is the hallmark of the time of flight MRA sequence. If you're going to remember anything about this, please remember this. Multiple 90-degree radio frequency pulses in short succession. That's going to help you remember the key points about a time of flight MRA sequence. So the first point is that it's going to have a very short TR. So what is a TR? So TR is the repetition time. Remember, we're not just doing this pulse sequence once. We have to repeat it many times in order to generate an image. And the repetition time is defined as the interval between these repetitions. And generally these pulse sequences, right, they're starting with a 90-degree radio frequency pulse, unless it's inversion recovery or something like that. So the repetition time is very short. Remember, whenever we have a short repetition time, that's going to introduce T1 contrast to our image. If we have tissues A and B with different rates of recovery of longitudinal magnetization, different T1 properties, that means that if we use a short repetition time, we're going to take advantage of those differences. We're going to highlight those differences. So a time of flight MRA is a T1 weighted image. So that's the second point I want to make. It's not a spin echo, it's a gradient echo, and it's a T1 weighted image. Okay, so fresh blood, fresh arterial blood, enters the slice retaining all of its longitudinal magnetization because it didn't see the previous 90-degree radio frequency pulses. It just came into the slice just before this next 90-degree pulse, okay? So it's going to have all of its longitudinal magnetization. Compare that with the stationary tissues. They're going to start with all of their longitudinal magnetization, but then that gets flipped into the transverse plane, so we lose it. It then starts to recover with a time constant of what? T1. But it doesn't have that much time to recover longitudinal magnetization. And so the next 90-degree pulse comes in and it just knocks it down again. And by tightly spacing these 90-degree radio frequency pulses, essentially what we're doing is we're decreasing the amount of time for recovery of longitudinal magnetization. So that's how we're essentially suppressing the longitudinal magnetization of the stationary tissue. So the fresh blood has tons of longitudinal magnetization, but the stationary tissue has very little longitudinal magnetization as a result of the preceding tightly spaced 90-degree radio frequency pulses. So this is the difference that we're hoping to visualize. But remember, we can't directly visualize differences in longitudinal magnetization. What we have to do is take those differences and flip it into the transverse plane. So that's what this next 90-degree radio frequency pulse is going to do. It's just going to take this difference in longitudinal magnetization and translate it into the transverse plane so we can see it. So how do we suppress veins? So, well, sorry, I kind of spoiled it. So there are no veins on this image. So this is a time of flight MRA image, a 3D maximum intensity projection. And we see the internal carotid artery here, and then we see the middle cerebral arteries laterally, and we see the anterior cerebral arteries medially. We see the vertebral artery to the basilar, to the PCAs. So tons of arteries, but no veins, right? There's no superior sagittal sinus. There's no transverse sinus or sigmoid sinus or jugular bulb. It's all arteries. So how are we doing this? We have to somehow suppress the signal from the veins. The way that we do that is by applying a saturation pulse to the volume above the slice that we're interested in. So this is really interesting, at least to me. Remember, veins are going to flow from the head to the heart. So in general, they're going to be flowing in a caudally directed orientation. They're going to go from the head to the heart. So if we suppress signal from the volume above the slice that we're interested in, we're going to suppress signal from the veins that would otherwise flow into our slice, and we would see them as bright on this time of flight image. So check this out. So we tune the radio frequency coil to excite a volume of tissue above the slice that we're intending to image. Let's say we're intending to image slice 7. So we excite slices 8 and 9. So that's going to convert all the longitudinal magnetization of 8 and 9 into transverse magnetization. So we have no more longitudinal magnetization, right? It's all transverse now. Next, we're going to apply what's called a spoiler gradient. We're going to talk more about gradient magnetic fields when we discuss diffusion. But for now, just know that when we apply this gradient magnetic field, essentially what it's going to do is dephase all of the spins and destroy the transverse magnetization. So as a result of exciting this volume of tissue above the slice that we're imaging, we don't have any more longitudinal magnetization because it's been flipped into the transverse plane. And we don't have any transverse magnetization because we've spoiled it with this gradient magnetic field. So we've essentially destroyed signal from the veins above the slice that we're imaging, as well as all the other tissues too. Shortly afterwards, the radiofrequency coil is tuned to excite the intended slice to be imaged, slice 7. The tightly spaced prior 90-degree RF pulses suppress longitudinal magnetization from the stationary tissues in the slice. Remember, that's what we were talking about in the preceding slides. This is how time-of-flight MRA works. We have multiple tightly spaced 90-degree RF pulses, which prevent any significant recovery of longitudinal magnetization from the tissues that stay in that slice, the stationary tissues. That's how we suppress signal from the stationary tissues. So now we've suppressed signal from the stationary tissues. So let's consider what happens. So the arterial blood moves into the slice. Here it is moving into the slice, and it has all of its longitudinal magnetization. So here's the artery, it moves into the slice, has all of its longitudinal magnetization. The venous blood also is going to move into the slice. So here are the veins, but remember, the veins, their longitudinal magnetization has been suppressed. That's what we did with this preceding excitation of the volume above the slice. So they're down here with the stationary tissue. So even though the veins move into the slice, they don't have any longitudinal magnetization, and therefore we have selected only for the arteries, specifically the cranially directed flow. Can you have bright signal on time of flight MRA that's not due to cranially directed flow? So the answer is yes. If you have something with a very short T1. So remember, we have a very short TR in time of flight MRA. These tightly spaced 90-degree RF pulses imply a very short repetition time. And whenever we have a short TR, we're going to generate T1 contrast. So if you have a tissue that has a very short T1, meaning it recovers its longitudinal magnetization very quickly, even though we're not giving the tissue very much time to recover, its T1 is so short, it still recovers a decent amount of longitudinal magnetization. As a result, when we do that next 90-degree RF pulse, there's still going to be some signal associated with that short T1 tissue. So this is what's known as T1 shine through, okay? And this is something we have to be careful of. When we're looking at a time of flight MRA, we shouldn't just assume anything that's bright is flow. It could also represent tissues with a very short T1. So how would we figure this out? How do we distinguish T1 shine through from, an aneurysm or something? So this is a time of flight MRA. How do you recognize that? Because the arteries are white. So here are the internal carotid arteries and the basilar artery. Here's the internal carotid artery as well. So the question is, what is this thing here in the left sphenoid sinus? Is that an aneurysm? I mean, probably not. It looks dependent. It's probably just some like proteinaceous gunk, right? So because we don't think that's an aneurysm, what we're going to do is we're going to go to the pre-contrast T1 and see if it's bright on that. And indeed it is. If we look at the pre-contrast T1, we'll see that that dependent gunk in the left sphenoid sinus was T1 bright. So this is not flow, cranially directed flow. This is not an aneurysm. This is just dependent fluid in the left sphenoid sinus that happens to have a very short T1. This is T1 shine through. Don't call this an aneurysm.